I'm ready whenever you are.
Okay. So it is my great pleasure to welcome Professor Matthias Niessner today. Matthias is a professor at the Technical University of Munich, where he leads the Visual Computing Lab. Before that, he was a visiting assistant professor at Stanford University. His research lies at the intersection of computer vision, graphics, and machine learning. And he's particularly interested in cutting-edge techniques for 3D reconstruction, semantic 3D scene understanding, video editing, and AI-driven video synthesis. Today he'll talk to us about learning non-rigid tracking, and I'll not take more of his time and let him take over and lead the discussion.
Yeah, thanks a lot. Thanks, Vasilis, for the introduction. I want to start with a very small anecdote, and this is partly the motivation of this talk. So I had a couple of interviews for PhD students recently, and I asked them how to compute normals in a depth map. And this is a standard thing you would do when you capture RGB-D data with the Kinect, you have a point cloud. And I was hoping some sort of answer, right? You compute a cross product and you normalize it based on the forward differences and stuff like that. Or you're computing a nearest neighbor search in the point cloud, you do a PCA, right? And you figure out what the normal is this way. But the standard answers I'm getting these days is, well, you just use a neural network, right? You feed in the depth map and you predict the normal map as an output. And as trivial as it sounds, there might be some truth to it. And I'm not sure if the students got it, because next time when I ask this, how to get the ground truth data, I was like, yeah, it's in the data set. We don't know, it's just there, right? But I think there's some truth to it. And one thing I would like to talk a little bit about, when you, for instance, thinking about the edges of the normals, right? There's some prior. And the question is, can we combine the advantages of the two worlds? Can we go ahead and compute the things where we know how to compute a normal? And sometimes you have like wrong normals and like edges and occlusions and so on, then you don't know quite how to compute it. In this case, maybe a neural network could help. And I want to talk about this specifically in the context of non-rigid reconstruction. And the reason why I think this applies here very well is, if I'm going to show you a non-rigid reconstruction that is not very well reconstructed and has holes, it has misalignments and stuff like this, you can immediately see it. So I have a very good prior of knowing whether it's a good reconstruction or whether it's a bad reconstruction, right? So in this case, like there's some high level understanding that me as a human I have, but my standard non-rigid optimization doesn't typically have. So I wanted to give you a little bit of first background about the task. I mean, I know a lot of people here are working in similar fields, specifically, I guess, humans is very popular these days. But the task that I'm talking about is generic non-rigid reconstruction, where we don't have any priors to begin with, right? So in this case, there was the seminal work of dynamic fusion by Richard Newcomb. It was like 5 years ago, and the idea was you had a depth camera, so you had a Kinect basically. You had let me see if this works. You had some input of the depth frame. They didn't actually use the RGB; they just used the depth data. And what they did is they accumulated this data. They computed a non-rigid warp, and based on that, they accumulated all the RGB-D frames together, and they got this final reconstructed canonical pose, and they could warp it into every frame. Essentially, how this non-rigid reconstruction works, the first step is what you do is you do non-rigid tracking. So in this case, you have some sort of template, you have deformation graph maybe on the template, and you're trying to align your current model with respect to another input frame, right? And in this case, it's a human, right? There's some non-rigidity going on, so we have to figure out some sort of warp field. And the way to do this is you have to optimize for the tracking. And tracking means typically there's two terms, right? You have a data term that tells you, try to make sure that every point projects to another point and try to minimize the distance. It's like an ICP in a sense. And then you need some regularization, because otherwise it could very well collapse. And regularization could be something like, try to stay locally as rigid as possible or something like that. And there's a lot of different fancy optimizations and regularization terms you could apply. I'm just going to give a very practical example. What I just described, this stay locally rigid. This is what this as rigid as possible paper was proposing. It's actually a paper from 2008 from Olga Sorkin-Hornung. And the idea is that you parameterize deformations as a rotation matrix, right? This is this R matrix and as an offset. So you have 6 degrees of freedom per deformation node or per vertex, depending on how you parameterize it. And then you have a fitting term and making sure that all your source and target correspondences are going to minimize, right? So this is actually very well known. There's nothing new here. What we have done, this is like, what people have been built up over the last, well, like 15 years, I would say. And the challenge mainly then in practice is finding these good correspondences. And the other challenge is how to optimize the whole thing. So when we're talking about optimization, you can use a gradient descent optimizer, right? So you're computing the partial derivatives with respect to all of these local rotations and offsets, right? If you're doing this with a gradient descent optimizer, you will quickly see it doesn't converge so well. So typically use a second order method like Newton's method. Newton's method in practice is a bit harder to implement because the Hessian is difficult to compute. So people mostly use Gauss-Newton optimizers. And then eventually this leads to, you have to solve this linear equation system for each Gauss-Newton iteration, which is, here we have 2 times JTJ. J is the Jacobian matrix. We have some delta vector, and we have here the gradients as a residual on the right-hand side. So probably most of you have seen this slide. That's the trick. When I ever show math, I show math that everybody knows. That makes it a bit easier. But I think there's a lot of interesting things going on, like how to solve this system here efficiently. Some people use parallel solvers on the GPU. There's different preconditioning schemes. And this is a few things I want to talk about in this talk today, how to make exactly this part more efficient. But assuming we have solved this non-rigid tracking, right? So we know this warp field from current frame to possibly the canonical model. Then what we do is we update a canonical template. So we basically warping all the frames into this canonical model, right? And then we do some volumetric fusion there in order to build up this canonical. Practically, this is kind of this iterative loop. So what you have is often you have an implicit function like a assigned distance field, SDF. What you do is you have a assigned distance field, you currently extract some sort of surface out of it, you render that surface as a depth map, then you compute here this non-rigid tracking I just described, then you optimized it, or first you find correspondences, then you optimize it, and then you integrate the current frame into this global shared canonical pulse model, right? And then you iterate every frame, you do this again, right? Every frame is one loop here. And when you do this, you get what I shown you at the beginning. You essentially have this warped model. This is the current frame. This is this canonical shape that gets more and more data as we integrate. And despite the optimization, which is pretty costly to do, we have a lot of unknowns. We also have a lot of residuals here. A big challenge is, of course, finding good correspondences, and we will very quickly realize this is a highly nonlinear problem. So we need very, very good initializations with respect to the previous frame. Typically, this is how these online methods like dynamic fusion or so work. They need basically the initialization from the previous frame in order to get in good initializations. So one naive thing we have done at the time, this was a paper at ECCV16. We thought, well, if you're doing this just on the depth, it's difficult to find good features. So what we did is we added sparse features, specifically SIFT features, in order to deal, for instance, with planar surfaces. So here we see an example of volume deform, where here we have the color input, right? We're computing SIFT features. This is a very planar surface, right? So like any depth ICP will fail here, especially in the non-rigid case. I mean, it's doing something. There's some geometric detail, but not that much. But if you're adding the SIFT correspondences, you're just getting you're getting better results. And of course, this was 2016. This work has already been, it has been done for quite a while. It's already old, so to say. Nowadays, you wouldn't do this, of course, with SIFT correspondences anymore, but rather you would go ahead and learn these correspondences. And this is something we have done in a very recent work at CVPR. This was deep deform. So the idea was we have here a source key point, right? And we want to find where is this key point in the target. So there's some non-rigid deformation going on here. It's not specific to a human. It could be anything. And what we would like to do is we would like to have kind of a heat map where this point would appear here in this frame, right? And we want to learn it. So basically, we want to figure out some sort of maybe fuzzy prediction where this point could be in this image. So this part of the backpack would be roughly here, right? And we'll have to learn this. And what we've done is we've taken a convolutional network, and this is how you typically approach these kind of problems. So you have a source and a target frame, right? There's a little red dot here in the middle. This is like the center of this image. And what we did is we have a Siamese architecture here with an encoder. we have a bottleneck layer. These two encoders here share the same weights. And then we have a decoder, and we predict a heat map of where this point would be in this image here. Right? This is pretty much what this heat map here is doing. And we have a couple of skip connections in the architecture, but more or less it's a UNet, right, with a shared with two shared encoders. And then what we do is we have the important thing here is this: we have a binary cross entropy loss that tells us is for every pixel independently, is that the point we are looking for? And then we also have a softmax loss that goes over the entire image, because we now know that this point has to be somewhere here, or we're assuming it has to be somewhere here. And then we're just saying, okay, force one pixel to make the right prediction. And by combining these two losses together, we actually get pretty good heat map predictions. This is in a sense very similar to what dense pose and these kind of things do specifically for like human joints or so. We can do this for arbitrary key points. I mean, the network architecture is a little bit different, but the key concept here is relatively similar. There's one caveat I kind of ignored, like this softmax loss here assumes that we know that this point would be here somewhere in the target. Because that is not the case, we have also visibility detection. So we have another binary cross entropy here telling us, is this point actually in the target or not? So give me a yes or no answer, did we see this point? And if we do see it, in the training, we simply mask out the losses here, right? So this helps actually quite a bit. So if you combine these two ideas, you can train this network both end to end, of course, and you're gonna get pretty good heat map prediction. So at the end of the day, when you train this, you're gonna get predictions that look roughly like these ones. So here we have the reference, this is our source, and this is our respective target. And we run the network for each of these source points once. This is one forward pass for each key point we want to find a heat map to, right? So this is one network pass, this is one network pass. So in this case, we have 5 network passes per frame here. And if you animate it, right, we get something like this roughly. So we see we get relatively good key point predictions here. It is fuzzy, right? It is a softmax prediction that we're making, and here it's kind of a visualization of whatever the softmax scores are going to be. We also have we have a few more sequences here. Again, this is completely unspecific. There's no prior about humans, no prior about clothing. This is a generic non-rigid prediction. So it's entirely driven to whatever data you're feeding in. Here's another example. This is kind of what we're getting here. It's actually pretty stable. So even if you think about it here, there's not a distinct feature here, but this key point here is relatively stable here on these shorts. Okay, so this is roughly how this works, right? So now we want to do non-rigid reconstruction with this. So now we have this canonical shape. We have a depth term in the same way. And now what we want to do is we want to combine the traditional non-rigid ICP with these feature terms. So now we have the canonical shape. We have one reference image. So we take this one reference image and we make predictions to the current frame with our CNN that we just had, right? And this is what the network here is doing, basically. We're running the network for each of these points. I can run it again. You see this red bottom dot here is kind of jumping around. Let's jump it around again. And you see where we're making the respective predictions on the target. And they look actually pretty reasonable. I hope this is actually, Zoom does it in a reasonable way. But we just basically, for a bunch of random points, we're running this network. And this gives us a bunch of predictions at the end of the day. Okay. And then we're taking these two terms, the feature term and the depth term. We have now these heat map matches, right? We map them onto the warp model, and then we have our fitting term, which is now composed of 2 individual terms, the ICP term and the CNN term. And then we just add these two up, and we have our regularization term. In this case, we're using a deformation graph that embeds our model, and then we join the optimizing that. And our reconstructions at the end look something like this. Right, here we have our input. This is our warp model, and this is the canonical shape that is in this canonical first pose. So if we are comparing this to dynamic fusion, well, we finish the sequence quickly. But if you're comparing this to dynamic fusion, the thing what's not so surprising, especially in like challenging regions like hands, traditional depth and ICP terms are pretty challenging, right? Because they just don't have so many geometric features, especially when the depth resolution is not so high. So in this case, it's not surprising that these kind of learned features that we did with our CNN are actually quite good in terms of finding good correspondences. Also, if we are quantitatively evaluating this, we have here, this is on a benchmark. I'll talk later about it, what benchmark this is exactly. But on this benchmark here, we have a deformation error that tells us for every deformation node, how close are you with respect to the ground truth? And this is the geometry error that is basically with respect to the ground truth deformation, with respect to the ground truth geometry, how close are you? Both is in centimeters. We're comparing here against dynamic fusion. I should say we spent actually a lot of time, and we're pretty confident this implementation replicates what dynamic fusion is doing. So the dynamic fusion implementation is not public, but we compared them on a bunch of the sequences that Richard gave us a while ago, and they give roughly the same results. I would say we're a little bit better even. We're a little bit slower. It's not meant to be online in this case, but it's giving pretty good results. Then what we tried is we compared against volume deform. This was the original code that we had a while ago. This one performs actually much worse, but that's more an implementation thing, that the implementation is just not as robust, right? If you're implementing this yourself, you will find you have to tweak a lot of things like thresholds, normal thresholds, correspondence pruning, and stuff like this. All the hard part that people typically conveniently, ignore in a paper. If you're looking at it in a benchmark, you see very quickly these things actually make quite a difference. Then what we also tried is we tried this dynamic fusion implementation, and we tried to use existing descriptors. In this case, we used one of our previous papers, 3D match. So we trained the sign distance descriptor on sparse key points, and we try to use these sparse key points to get matches. And this is actually how we started out. And as you can see, it actually made the results even worse. And there's a specific reason why it made it worse. And the problem is, if you have two frames and you randomly detect key points, the chance you're detecting exactly the same key point for a non-rigid scene or for a non-rigid frame is just very low. You're not going to detect exactly the same one, right? If I move my hand here, right, like I will not detect consistent key points over frames. And this is why this like key point-based method where you detect independently didn't work so well. And ours, in a sense, is better because we have key point first, right? And you predict this heat map, and then you know exactly where you are. And if you're looking at this quantitatively, we get actually, quite substantially better results in terms of both deformation and in terms of the geometric error. Okay, so this is roughly how you can do. Well, you didn't do too much, right? Basically, what we're doing is we're using a network. We're learning correspondences now. We're using these correspondences for non-rigids, and we're getting better results this way. Here's another example, especially in like planar regions, right? I mean, dynamic fusion, when you have an ICP term, it can't deal so well with these planar regions. So eventually, this one just falls apart. This is kind of how falling apart looks like. I'm not saying we are solving all problems, but we are on average, we're substantially better. Here we have another example. And this is a comparison to Calvin Guo. I think he's at Google now. This was from Yevin Leo's lab in Tsinghua. So these guys, they use the photometric term as well. We got actually the code from them. It works actually pretty well, but it's still, in challenging cases, the learned descriptors are just going to be better whatever you have handcrafted. It's just how things go. Yeah, so this is great. We're getting pretty good correspondences. There's one little minor detail that I ignored so far. Of course, all this stuff has to be trained somehow, right? And this, I think, was a big problem in both vision and graphics, actually, that a lot of these non-rigid papers, including our own, so I can blame us too, were like cherry picking the results, but we didn't have a concrete benchmark to evaluate on it. And this is one thing we actually introduced along with this paper, and we wanted to do both. We wanted to have enough data such that it's trainable, but we also wanted to have a hidden benchmark where people can submit their results, and then you automatically see how well your reconstruction goes. And we don't have this like, oh, I can do this sequence better, you can do that sequence better, and so on, but we have an objective evaluation, actually. So what we've done is actually, we actually had to spend a little bit of thought on it. It turns out it's not so easy to annotate non-rigid sequences, because practically what you would have to do is annotate where every pixel from one frame goes into the next frame. It's in a sense like optical flow, right? You have to know where every pixel moves over time. And this is challenging. So what we did is we first captured some data. We used an iPad with a structure I/O sensor. It's basically a connect on the iPad. The color camera though comes from the iPad. So we captured a bunch of sequences. We hired people to help us capture sequences. I'll go to the numbers a little bit more. And then we did a thing what we call semi-supervised annotation, meaning that some stuff we annotated and some stuff we inferred. The first thing we annotated was the masks. So whatever the non-rigid object of interest was the first thing we annotated. In this case, we annotated the person here in the foreground. We gave that person a label. As you can see it, we first get an over-segmentation here. We use, I think it was quick shift what we used. I have to double check, but I think it was a quick shift segmentation, an over-segmentation, and then we annotated the segments in 2D and got the mask this way. And you see, it's pretty accurate actually. We did this for quite a substantial amount of frames. And once we had the masks, now we looked at correspondences. In this case, we did a sparse annotation. So what we did is we selected a bunch of key points in frame pairs. You can see this here. And well, I can show it again. It was a little bit fast maybe. So we click here. This is 5x speed, right? This is obviously much faster than it was in practice. We get a bunch of correspondences here, right? And then what we do is we actually already run a non-rigid optimization based on these sparse correspondences, and the annotator saw this in the preview. And this was pretty important. So we wanted to get this dense alignment. And we did this already by running an Arab regularizer. So there's a bit of a bias in the data set. But we already got this dense alignment in the preview. So basically people put a bunch of points there. They clicked on align, then it aligned the stuff. And once it was aligned, then they could either add more points or say it's okay, right? So they could reject or accept it basically. Yeah, and this gave us the dense alignment, but we didn't do the dense alignment ourselves, right? So that in a way we didn't like annotate every pixel, but we rather had sparse annotations, and we used the non-rigid registration with the ground truth correspondences for some sparse points until the user said it was okay. And we had a relatively elaborate verification process. So we had a bunch of TAs or RAs, PDs that helped us here. So we hired actually a bunch of people. In total, I think we had 8 or 9 people that were doing this for quite a while. They were doing these annotations. Then we verified it again. And whenever we weren't happy with the results, and this was very easy to do because we just looked at the final alignment of the reconstruction, we said either it's okay or not okay. And if it was not okay, we send them back to the annotator again, right? And this was a loop that we iterated on. So we spent a bit of time doing this. We captured actually quite a variety of data, I would say. Most of them are like, single person holding something up. We have clothing, we have a lot. People, of course, we have a lot. Backpacks, pillows, beds, whatever. We have a detailed statistic in the paper, but there's a bunch of stuff actually in there that we recorded. So if you're looking at the whole statistics of this data set, we had in total 400 sequences. They were all unique sequences, so we didn't like record the same thing twice. We roughly had close to 400K, 390K frames, RGB-D frames. We have about 5.5K dense alignments, 4.5K object masks, 150K sparse samples, and then we also annotated occlusion points. That's something I didn't mention right now, but remember we have this occlusion network that tells us if a key point from one frame is actually visible in the next point. We also marked these things that were basically disappearing. And this actually helped us in terms of the performance quite a bit. So I think this is an interesting first step for a data set for this area. This hasn't been done before, and I think it's pretty important because there hasn't been so much progress in that field, I think, that it could have been, right? Especially when we're talking about data-driven methods. We also have an online benchmark right now. So out of this data, we released 340 as training. We released 300 as validation. For both training and validation, we give the data, the labels out. However, for test, we only give the sequences out, but we don't give the labels out. So you can run your method on the test set, you submit it to the benchmark, you get an automated result, and then it's either you get some number back in terms of our metrics, but you don't get the labels. So and yeah, we're trying to make people not submit too many times. Like I think 2 weeks is our current limit. And then we evaluate with respect to reconstruction evaluation. We have geometric error, we have deformation error. That's already something I mentioned. We actually also introduced a flow evaluation. This is pretty new. We haven't actually done this too much ourselves. We ran the state-of-the-art optical flow methods like PVCnet and FlowNet. We gave them as a baseline out. We haven't seen a lot of people trying it out yet, but it's actually interesting, right? There's not a lot of flow evaluation methods for indoor scenes, right? I mean, you can do flow evaluation on synthetic data like flying things or Sintel. You can do it on Kitty, but then anything like indoor dense, you don't have anything, right? And I think this is kind of an interesting benchmark that came out for free as a site. You could try that. We actually have a few projects working on this here, possibly also using the depth. There might be some interesting things coming out. Anyway, I think it's a cool data set. I think if anybody's interested, feel free to try it out. I wanted to talk a little bit further though in terms of the global overarching goal, because when I started the talk, I wanted to learn non-rigid tracking. Or even reconstruction. I want to learn both. So far, what we have done is we're learning non-rigid correspondences. We're doing this offline, right? And then we're doing some optimization afterwards in order to get the non-rigid alignment. And we have supervised data now, which is great. So everything is supervised. This is nice. But it's still a bit unsatisfactory from a methodology standpoint, because we don't really care about the correspondences in terms of our final loss, but rather we care about how good is the final non-rigid alignment or even the final non-rigid reconstruction. So these are the two drawbacks of all of these methods I've just explained. So optimization at the moment does not inform the feature match. Like basically, this is a thing that's it's so funny all the time. When we started working with like 3D match and geometric feature matching, we got like numbers that were like orders of magnitude better than SIFT or SURF. But when you put it into a SLAM system, like typically the SIFT and SURF features were still better, which was very surprising, which basically means that our loss functions or whatever we had, or evaluation on the per feature matches, was not really indicative in terms of the final performance of the reconstruction system. And this is the same here too, in a sense. The problem is basically we're learning correspondences, but we're not learning the full reconstruction yet. And what I believe is, right, we should obviously look at both. And we ideally want to have gradients from the reconstruction or from the non-rigid tracking to help us guide what are good correspondences and possibly automatically filter out wrong correspondences, right? Another drawback right now of this method is it's horrendously slow. You're basically running a single network for every correspondence. Well, I mean, one network forward pass is pretty fast, but if you have to run like 500 of them per frame, then it becomes pretty slow, right? So this is not real-time capable at this point. So this is a big drawback. So we decided to look a little bit more into the optimization. And I mean, of course, this is a very hot trend. We're not the only ones doing this. Also from, I guess from Michael, from your group, a lot of people looking into losses for optimization and so on. And we did this for non-rigid. So we want to basically figure out how to get gradients backpropagate through the optimization, and because of that, get better features. So one of the first projects, this was also CVPR oral this year. We wanted to do non-rigid frame-to-frame tracking. We looked at a simplistic case here. We didn't like do a fancy deformation graph for this one here. We just looked at, give me RGB-D frame, source and target, and then deform the grid such that you can align the two. So basically, you have this frame here, right? You have that frame here, and then you want to find this non-rigid alignment. So what we've done, we came up with an architecture. Well, of course, we're using neural networks. We have a source frame, we have a target frame, we have a shared encoder. Actually, this is a bit of a misleading figure here. These are actually not fed into the same. There's the same encoder is there twice. They do share the weights, but they're not merged into the feature channels. There's two streams of features. One of them for the source and one of them for the target. And then what we want to get is we want to get features for the source and features for the target. And now we have an optimization. I'll get to this in a second. We're feeding both of these features into the source and the target. And the goal is to minimize, based on the ground truth error, and I'll get to this also in a second, based on the ground truth error, we want to make sure that based on these features, we get the optimal deformation graph at the end of the day that aligns it with respect to the ground truth. And deformation graph is not a real deformation graph here. It's just a grid of images in pixels. So let me go into a little bit of details here. So these ones are basically deep features. This thing here, these are deep features. This is what we're using for matching. we're fitting these correspondences, so to say, or these deep features into our Gauss-Newton optimizer. You know that we're just using Gauss-Newton here. The optimizer is fixed. The linear steps for Gauss-Newton are optimized with PCG in this case. I'll talk a little bit about this one. We're gonna get some delta update on the graph, and based on the graph, you're warping the features here, and now we're getting the warp correspondences here, and we're basically comparing warp correspondences from here with the target correspondences, and we're doing this based on a ground truth loss on the graph. Yeah, and in practice, the ground truth loss on the graph is given by the data set, so this is a fully supervised process. We're just trying to find the nodes of every pixel where they're being deformed, or the deformation graph nodes. They should stay close to the ground truth. This is just a standard explicit supervised loss here, right? And we're going over all of the pixels, so we're trying to make sure all of them align perfectly. So now the interesting thing here is, and if you're going quickly back here, what is learnable is basically all of the stuff in this network that produces these features. This is the learnable part. This part afterwards here is a fixed function part. This is our optimizer. We have n Gauss-Newton steps, and in the Gauss-Newtons, we have the inner loop of PCG, and we have k PCG iterations, right? So what we're asking right now is, how can we get the best features here such that our optimization gives us at the end the final alignment? So we don't care about really what's in here. We only care about give me good non-rigid alignment at the end of the day. And the way we can formulate it is because we differentiate through the whole thing. Okay. Yeah. So now, how do we do the inner part? So if you're quickly going back here, this is our Gauss-Newton, right? So this is our delta here. This is our update vector. So this one becomes JTJ becomes our systems matrix, and this JTR becomes our right-hand side B. So if we have here, this is JTJ here. This one is JTF basically. This is our gradient, right? And this is JTJ. This is what we want to solve with PCG, preconditioned conjugate gradient descent. And all you do is you go to Wikipedia. Basically, you check out the PCG method. It's a bunch of matrix operators and matrix vector operators, and you just want to make sure that all of these things you can write down in PyTorch, and then you can differentiate them. So in a sense, it's actually pretty straightforward, because basically what this is it's like a PCG loss, right? It tells you if you're optimizing with these features, how good is your loss? And then you're asking, how do I need to change the features such that the PCG loss becomes lower? Like your optimization is make the PCG loss better. And now we thought a little bit about how do we make PCG efficient. And if you want to make PCG efficient, you're looking at the P part, you're looking at this preconditioning. So in practice, you're not solving AX is equal to B, but you're rather solving some preconditioning matrix M inverse times AX, right, is equal to M inverse times B. So this preconditioner, there's a lot of different preconditioners you can apply when you're running an optimization. And based on our previous works, we realized, well, okay, we need a preconditioner. They makes just a huge difference, and we didn't know which one to use, so we tried a bunch of them out. So typical choices here are incomplete Cholesky factorization, right? We can do block diagonal. Yeah, the standard thing is Jacobi preconditioning. That's just using the inverse of the diagonal matrix. That's the easiest one. It comes at a cost, right? So the more effort you're putting into your preconditioner, the fewer iterations you need in the outer loop, but every iteration becomes more expensive because you have to compute the precondition. And there's an extreme case of a preconditioner. If I had my dream preconditioner, I would basically know how to invert A, right? If I can invert A and M is equal to inverse of A, then I'm done with solving it, right? I don't want to compute an inverse. Computing an inverse is a bad idea, and it's very costly. Yeah, but it's what I would love to do. So one question is also like about the sparsity of M. Do I want to have a lot of entries in M, or do I just want to have a diagonal matrix here in M? And there's a whole literature has been going on for a long time, like what preconditioners to choose. And we tried a bunch of them out, a bunch of them worked better, a bunch of them that worked better took also more time. But we thought, well, why can't we just learn that? This is a very problem-specific setup. And so what we thought is, well, we're simply learning our preconditioner. And in this case, what you could do is you can say, give me A, feed A, my systems matrix, which is JTJ, feed this into a network, and then predict basically a preconditioning matrix. Right? So this is one thing that we should do here. There's a few things we should be careful about M. M should have some properties. What we did is we basically made sure it's symmetric positive definite. And the way you do this is you just predict a lower diagonal matrix first, and then you can compute M inverse by L times L transpose, right? And yeah, this network predicts L, and then we have a hard-coded L times LT that gives us M inverse, right? And then we have our PCG layer that I just mentioned. Now the PCG layer has also an M inverse here, it has an M inverse here, and it gives us some X as the output, right? And now there's a bunch of variations. One variation is basically now how many things in this matrix allow the network to predict. We can make it sparser, we can make it denser. And I will show you in a second what the implications here are. But now what we do is we just have this PCG loss, and we can train this conditioning network jointly with the rest, and can just say, well, whatever gave us the lowest PCG error, this was the best matrix conditioner, right? Best matrix preconditioner. So give me A, learn the preconditioner. It's a problem-specific preconditioner. This is not like, oh, this is like for every optimization problem, use the same preconditioner. It's based on our data, on our training set. What is a good preconditioner for this kind of data? And this actually turns out it helps massively. This makes a huge, huge difference. So if you're comparing this on a graph here, we have in here, this is the number of PCG steps, and this is the residual error basically you're getting. We just said 10 to the power of -6 is converging. And the idea here is, well, if we don't use any preconditioner, then we need roughly maybe like 45 iterations, right, until we converge here. This is this curve here. If we're using block diagonal, we are here. If we're using incomplete Cholesky, we are here. If we're using our condition net only in diagonal, then we are here. Oh, sorry, condition net sparse, then we're here. Then we have the block diagonal, then we're here. And if you're using a denser version, then we are here, right? So it's pretty interesting. So compared to the original, like let's say the best preconditioner is incomplete Cholesky, that's like 37-ish or so. Here we're like at 12, right? We actually get like a speed up of like 3x or so in terms of number of iterations that we have to do. And I think that's quite interesting, right? Basically, we're learning, it's basically learning how to do PCG, right? We're learning what is the best optimal PCG step based on that loss, based on that data. This is not a generic PCG. You can use it everywhere. You have to retrain it on a specific data set. But it's at least better than having no priors, right? It's a very easy way to get priors in your optimization problem. Yeah, we have a couple of comparisons here. Again, we compared against our dynamic. Oh yeah, and this is also trained on the deep deform data set. Like this is the same scenario that you've seen before. So we have the ground truth actually, right? So this is still a supervised problem. So this is our knowledge alignment results. Again, this is a very simplified framework here. There's no complete reconstruction framework. And the deformation graph is just the pixel grid. We have a source frame, we have a target frame. Yeah, and then we do like compare against dynamic fusion, and we show we're better because we're not only converging faster, but we're also more robust because our network helps us here, right? We have more results here. I guess this is a reconstruction of myself. And we see we're getting quite good results. Okay, so far, what I really liked about this method is it actually, there's a couple of cool insights. I mean, I couldn't go into all of the details here right now, but there's a lot of cool insights in terms of what can we learn through the optimization. So far, we're only learning this on a 2D grid. So it's not generic deformation. It's by no means a complete reconstruction framework. So this was basically a relatively straightforward toy case where we focused on the theory behind what can we learn and we optimize. And I think a lot of these insights, by the way, are applicable to other problems too. We're kind of thinking about this too, right? If you're looking, for instance, at stuff like, I don't know, like want to optimize a simple model, fit it to a target point cloud, right? You could probably try the same tricks here. So what are the next things? Well, we want to essentially do a bit more. We want to combine. The one thing I actually thought first deep features are cool, but then I realized, well, maybe direct correspondence estimation could stabilize the problem. So this is something we wanted to combine. But we wanted to actually do a bit more here. We wanted to figure out not just putting these ideas into a complete reconstruction framework, but I think when you're talking about correspondence predictions, one thing you always do by hand is you're selecting the correspondences. you're selecting which is the right correspondence, and how much does it help your final reconstruction. And we do this by hand typically. And this is what we wanted to do here. It's kind of like an attention idea. So, right, for attention, you kind of want to see how important is every word in the sentence. This is what NLP people do. But we wanted to figure out how important is every correspondence, or is a correspondence an outlier and we don't want to use it. This is kind of what we want to do. And then we want to have a generic deformation graph where we could end-to-end optimize. Okay, so, and this is a project that's very recent actually. We put it on archive a few weeks ago, I think 3 weeks ago or so. And we call this neural non-rigid tracking. So the idea is scenario is now a full reconstruction framework, basically. We have here input frames, 2 input frames, and we finding correspondences. We are weighting correspondence, like this kind of attention idea, what I mentioned. It's not really attention, it's not an attention mechanism, but it's kind of inspired. And then we're figuring out which correspondences we want. Our solver is solving, right? We have a data term, we have a regularization term, same as before. And then we have a loss at the end of the day that says how close are we with respect to our ground truth, right? And the idea is now, this is a one-shot pass, so I can do this for all correspondences at the same time. And this weighting here is a thing we want to do self-supervised, right? We don't want to have a loss explicitly telling us, oh, this is an important correspondence, but we want to have the similar to attention, like multiply our weight with respect to the correspondence, and then try to minimize the overall non-rigid alignment error. And then we want to train this whole thing at the same time, right? We want to have gradient flow coming from here all the way to the beginning in terms of giving us good correspondences such that the optimization gives us good non-rigid alignment. This could mean I want to have a lot of correspondences and I filter out some outliers. I want to filter out possibly more outliers, but if I filter out too many outliers, then I don't have enough to constrain the model anymore, right? So there's a bit of an interesting back and forth. Yeah, so let's quickly go through it. We have RGB-D, right? Then we have a network here that does the correspondence and the weighting prediction. We're getting these correspondences. These are the good ones, the green ones, and the red ones are the bad ones. And then what we do is we getting these predictions here, right? These are the predicted ones. Now we filter out the outliers. Again, this is self-supervised learning. So we have outliers. Now we have this differentiable solver. It's operating on a deformation graph in this case. So we automatically sample this based on the current data. We get a deformation graph. Yeah, then we have the deformation graph here on the non-rigid object. And then we're optimizing it, right? So this is what we want to do, and then it's being optimized, and then we're running a bunch of Gauss-Newton iterations here again in order to get the final alignment. Okay, yeah, and the key is that we get these gradients here through. I have another diagram of this whole thing. So what we're getting is here input images, right? We have the depth, and the important thing here is 2 things. This solver here is differentiable. That means the correspondence predictor knows about what the final non-rigid warp should look like. We have these weights that tell us how important is the correspondence, and that is only just the multiplication on each correspondence, right? It tells us, oh, weight it down or weight it up. This is how we're weighting it in the optimization, but there's no explicit loss on this weight here. The only losses we have is we have a 2D correspondence loss. This is like, it's pretty much an optical flow term, right? It tells us in 2D how things should move around, but we're using the depth data to back project it. We have a graph loss that tells us don't move crazy around. This is the regularization term here. And we have a warp loss that tells us, yes, whatever you want to have with respect to the final target. And what you can do now is, you can of course so if you're thinking about traditional optimization, like what I talked at the beginning, you would just cut off here this whole thing in the middle. You would only optimize like a correspondence term here. Again, this is similar to a flow network. And this part here would be a fixed function that is not being part of the correspondence optimization. And now what we want to show is, but by having this end-to-end optimization, meaning adding these 2 losses here, we're getting better reconstruction results, because now the correspondences are informed with gradients through here, whatever we're doing here at the end. Okay, let's have a look at some results. I copied this one out of here out of the paper. This is an ablation study. Yeah, this is basically the different models we're using. These are the different losses. This first one here is, let's go on the evaluation metrics first. EPE is endpoint error. that means how good are our 2D correspondences. This is just measuring the 2D correspondences, back projected to 3D, check how good they are. This one is how good is our deformation at the end of the day. This is for every deformation graph node, how close is it to the ground truth. So this is kind of our proxy, and this is what we actually care about at the end. So graph error is what we care about. Both is in millimeters, so it's actually, you know, not too bad, like 6 centimeters, it's all right. So if you're basically using a flow network first, you're getting like 42, right? If you're adding this graph term here, if I'm going quickly back, like this term here, then it's already differentiating through the optimization, then you're getting a little lower. If you're using this warp loss in the beginning, you're also getting a little bit lower. Same counts for the graph error, but this one goes down a bit more, which is reasonable, right? That's what we care about. And now this part here, this phi, the psi is actually, this one is now based on if we weight the correspondences. Again, I like to call it, it's similar to an attention. It's not attention, it's not an attention mechanism, but it's the same idea, right? You just multiply the correspondences, how important they are. If you supervise that one, if you have an explicit loss, it goes down from 35 to 28 here, right? It's quite a bit. And the reconstruction goes actually massively down. It goes from 50 to 36. That makes a big difference. Like pruning out bad outliers and learning which ones to prune, that's a good idea, obviously. But it turns out when you do the self-supervised, that's even better. The self-supervised version is the best one here, meaning you don't have an explicit loss for the masking, but you're rather going ahead and say, let the final error decide which correspondences to take. And this is, surprisingly, it also helps the 2D correspondence estimation. And the answer is very simple, because it just masks out the one it doesn't want to optimize for, right? And this helps overall in terms of the absolute evaluation accuracy. So this is the ablation study we've done here. We also compared against the previous models. So these are the two handcrafted ones with dynamic fusion and volume deform. Again, our implementation of dynamic fusion is significantly better than the volume deform one, but this is an implementation detail. But we just wanted to show that our dynamic fusion implementation is actually pretty good. I would say it's probably better than the original one, but it's a bit slower. So yeah, we're getting actually, if you're using all of the stuff together, right, we're like massively better than the dynamic fusion one. We are a little bit better than the deep deform one, but we have to be careful here. The deep deform one has to run one network for every correspondence. So we are like 85x faster than deep deform, which is like pipeline-wise, that's like a massive simplification. Also, it's real time now, basically, right? So this makes a huge difference, which we should actually consider at the end of the day, right? And it's much easier to solve. Here again, deep deform is close. We are a bit better, but we are massively faster. If you're thinking about it this way, like in this case, we are basically matching, this is a softmax loss for every correspondence predicting where it is. And this one is basically a flow term that leads to the same performance. And if you're doing flow, you know that the first one is a much easier loss to optimize. So I think this is still a very remarkable result that it is so good. And it's much cleaner, actually. But actually, if you're looking at some visual results, we had many sequences where it did actually work better. And yeah, often like deep deform fails at the end of the day a little bit, right? And basically what it means is it propagates the error a bit too much, whereas ours, the new version now is a little bit better in the longer run. We have another example here. This is against mono FVV. I mean, that's the previous paper from Kaiving Duo. Dynamic fusion here, and you know, even they use that, you see here, they don't quite get the arms right and so on. But again, these are handcrafted features, and now we have an end-to-end optimization to learn the tracking all the way. Okay, so this is a bit of I want to summarize and conclude maybe a few things. So I've talked basically about 3 works here. Deep deform was the first one. I would say cool method, but good data set. Method is maybe not the strongest part here, but I think the data set is really strong. The CVPR oral here was pretty cool, I think, because it's basically looking at like learning preconditioners and stuff like this, which actually could possibly be applied to other problem statements too. And then here we're already going through the whole non-rigid tracking pipeline with this neural non-rigid tracking paper, and we're showing it's actually fast, it's very efficient, and we can kind of do the self-supervision to get rid of bad correspondences in a very nice way. So I think if you're concluding around here, what's really cool, I think, is we differentiated through the tracking, but what we have not done yet is we have not tracked throughout the reconstruction, right? If you're thinking about it, what would be cool is if I had like a GAN that just sees real examples of good geometric models, and based on that, you're learning gradients that tell you how tracking works, right? Just look at the final geometry, and it tells you how do you need to track to get this good geometry, like, or see something like a ShapeNet model, right? I want to have a ShapeNet model, but I only have RGB-D frames. How do I need to combine the RGB frames to get to the ShapeNet model? Something like this. So that what we're doing here right now is only looking at the tracking, but not at the reconstruction itself yet. And eventually you want to figure out how do we need to change correspondences, fuse data to make things better, right? So this generally, yeah, I think generally it's also interesting to learn priors in optimization. I mean, we're learning priors for non-rigids, right? That's one part. But I think this could be done for many other things too, right? This is just a single thing here. Yeah, I think generally if you're thinking about optimization, I think what's even cool is if I know I'm in the right local minima, I can run an optimizer. I can run Gauss-Newton, I can run LM, whatever I want to run, right? And this one actually, you know, we have done for a long time for real-time SLAM, for real-time reconstruction frameworks, because we just take the previous frame as an initialization. So we are in the right local minimum for most parts. And if not, we do some course-defined optimization, and eventually that's what we do. But I think the big question is, how do we know if it's the right local minima, right? I mean, this is like the holy grail of computer vision. If I only knew that, then a lot of things would be easier. And it's also not so easy to train a network to do that. Because if I knew how many local minima I would have to do is I have like a softmax and tell me which is the right local minima and just predict the right one, and then I start from there. That's kind of what I want to do, but it's not so easy to get these two frameworks together, right? So, but I think there's a lot of potential in terms of differentiating through optimization procedures. One thing is also interesting right now is at the moment, you're only looking at optimizing still features, but there's no neural network weights after the optimization. This, I think, is another thing, right? Like we have to be careful. At the moment, you could, all of the stuff I've just talked about is basically you using it as a loss. Yes, you're differentiating through it. You're getting gradients. You're getting better gradients because of that. But you're not really having weights afterwards. Like you don't have a neural renderer or so afterwards that tries to get a better reprojection after you optimize. So this is something that is a bit more tricky. And I think there's going to be a lot more research. Yeah, so I don't know if you're looking at non-rigid reconstruction, right? If I look at it, I just know it's good or bad, right? Based on the alignment, it's very quick. If I had a classifier telling me this already, and based on that, making a new proposal, which could be better, right? I just make proposals all the time until I get a good one that my classifier says it's nice. Yeah, then I can start optimizing with a traditional method there. So this is kind of what I would like to do, but it's of course a little bit harder because you don't know how many local minima you have, and the dimensionality of these spaces becomes pretty massive at some point. If you have like 1,000 unknowns in your deformation graph, right, that's quite something. You can't just brute force sample that. So I think, yeah, misalignment most of the time means bad local minima because you converge to something that is wrong. So yeah, I don't know. I think this is a pretty cool area. I hope there's going to be more connection between optimization and learning. How to get these priors in is still an interesting question. So yeah, getting back to my, I guess, original question. So maybe the student were right when you're saying learning these kind of things could help. Even if you're computing simple things like normal, some stuff I know my computation is doing wrong. If I have a network to tell me where my standard computation is wrong and kind of model these exceptional if statements in a sense in a generic framework, yeah, this would be helpful. For optimization, these are local minima, right? So this is something maybe to think about. I'm not arguing we should use neural networks for everything, but I think there will be an interesting combination between the two directions. Yeah, so with that, I would also like to thank all the people who actually worked on this. So these are, yeah, Alias did most of the stuff actually on the volume deform, on the deep deform. Pablo is now working on it too. Yang Li did the learning non-rigid optimization paper. And then Angela, Justus, Christian, and Michael were the collaborators. And I should say all of these guys, the students here did all their work, and I also stole their slides. So they probably deserve all the credit at the end of the day. I'm not sure how much time we have, but I'm still around for a bit, so we can still chat. And if there's any questions, I'm more than happy to answer them.
Thanks, Matthias. That's great. I really think it's exciting how you combine sort of classical optimization methods and geometric methods with deep learning. I think it's a very fruitful area. So can I kick it off with a question though?
Yeah.
So I'm curious about the deep deform data set, because I haven't looked at it carefully. But as I understand, what you guys do is there's some human annotation to get initial guesses, and then you do an optimization-based approach to get the non-rigid alignment. And have you benchmarked that to really get how accurate that is as ground truth? So I notice on some examples, it's a little bumpy, or some wrinkles on a t-shirt are missing. You could do the same thing on synthetic data where you have ground truths, or you could have some scanned rigid objects where you know them exactly, and then you could benchmark and get the accuracy somehow.
Yeah, good question. I mean, it's a high-level question. I mean, basically, how accurate can you actually get these annotations to begin with? I mean, like, again, what I would love to do is get every pixel accurate correspondences, but I mean, it's tricky. What we have done is actually we looked at the pixel errors, and we had actually two groups, right? One group was annotating, and then we had another group looking at the reprojections and looking how many pixels they were off from the guess, right? And they zoomed in to like n pixels. In the end, I think it was within like 2 or 3 pixels on this resolution. That does not answer your other question, like how accurate is the geometry, right? I mean, this is it's a missing thing. Like there's the other thing. What you have is you still have the sensor noise too of the depth map, right? This is another, like, yes, you can do this, what you suggested. You can use synthetic data. You can get this first error of the equation you can get out of. You can figure out how good is the annotation there. We haven't done that in fairness, but you would still have and you have another source of error where the geometry is inconsistent over time. I think it's pretty accurate, actually.
Well, it may be, it sounds like,
I would say 2-3 pixels, I think that's what we had at the end.
Right, so this may be problem for the optical flow piece of this, because the flow community's been working for years on really sub-pixel, like really accurate sub-pixel alignment. And people are just kind of driving that down. So if the data set is at the pixel level or above, then you may find it a hard sell for the flow community.
That might be true. I mean, in fairness, this is something we got out of it at the end. I mean, we wanted, what I cared more about is currently there's a lot of papers about non-rigid reconstruction, but in order to get all of these things to work in practical scenarios, we are light years away. It's just very far away. And I don't know, I mean, like when you have a lot of papers, they all say, oh, now it's working, now it's working, now it's working. At some point you have to get at least, I'm not arguing, we're like sub-millimeter accurate, right? Like this was not the goal of this data set, but we wanted to get a rough evaluation, and every method right now, including our new methods, they are nowhere near close to solving this data set. Like we're not actually bottlenecked by how accurate the annotations are. There's like at least 2 or 3 years of research ahead of us to get there.
So what do you think about synthetic data for this problem? Because then you would really have sub-pixel, perfect, accurate ground truth. You know, it might be, is it too expensive to get enough data?
So we're actually working on this right now. Okay. I think the synthetic data is very interesting. Basically what we're doing is we're having animated characters. It's very domain specific. The reason why we didn't start with this, we still want, we're not quite there yet, but we wanted to have like a practical demo that runs like on a phone eventually or something like this. And the problem you of course have, right, you have to deal with the domain transfer when you train on one or the other, but I like the synthetic direction a lot. I think this is a really cool direction, and I think it would be pretty stupid if we ignored it, right? So we should go that, but I think nonetheless, you still need some sort of benchmark on real data, and you need to do some fine tuning on real data eventually, right? So yeah, we do actually work on one data set. We have animated characters right now on synthetic data. It's very costly, and it's very tedious. Like you need to filter out what are good animations and bad animations.
Okay. Yeah, yeah, absolutely. It's a hard problem for sure.
But yeah, I mean, but I guess my point is right now, I mean, I think this community had a lot of drive like 5-6 years ago, and then we slowed a little bit down. Like, you know, like, yes, there was progress being made, but it's not like we don't have a real-time system that you can just use like Kinect Fusion or so was at the time that runs at the same fidelity. Like if you're comparing it to like things like, I mean, a lot of things you guys have been doing, right? Like Vibe or so on, right? These are things that work relatively well right now, I would say, but they're specific to humans. So how far are we away to making this one practical? And we're not even close to it, I think, right now, as a community, not just we. Like, I mean, it's a hard problem, right?
Yeah. Super. Okay, other questions? Please, please, please. Uncharacteristically quiet this afternoon.
Can I try one, maybe?
Go for it.
Matthias, also, I think like comparing the first one, deep deform, with a non-rigid tracker, could it be that the network also benefits that it sees all points together rather than you forwarding each point every time from the network and then each?
In practice, that's the same as having multiple points in the same batch, right? Because you just have more loss. Like the question is having more losses in one forward pass. Sorry, having more loss. You have multiple losses at the same time in one backward pass. Is the same as having splitting them up because it's just additive, right?
No, but I mean, for example, comparing network architectures, in the first one, you just forward one point, you get a correspondence, and then you go back, you give another point, you get another correspondence, and so on. But these points do not inform each other between them.
No, that's what I'm trying to say. They do. They do it across the batch. Okay, so they still see the whole image, right?
Yes.
Okay, let's say we have 2 points. You have one image, you take 2 points here, and you're running both of them, and you get 2 gradients, two SGD backward passes for both points independently, right?
No, I mean, not at train time. I mean, at train time, of course, you get lost for both, but at test time, for example, in the last network, because of the weighting and everything of this, I don't know, non-local, self-attention, whatever you call it thing, you kind of, the network has to reason for all correspondences jointly at the same time, not...
Yeah, but it's the same thing, right? Basically, it's a fully convolutional network, so you could shift it by 1.
Okay.
Right? It's literally the same thing. If you shift it by 1, like the network would share most of the input, but would do it for another point. So it would still have to make sure it's consistent.
Okay.
But if a fully convolutional network predicts you 1 point in the center, and then you're running the same network again, shifted by 1 pixel for the next point, is the same as running the network once, which is a little bit bigger, with the same conf kernels, with both, right?
Yeah.
That's what I'm trying to say. Like this depends on how you do the optimization. This only matters in the training. In testing, it doesn't matter at all.
Okay.
We've tried this not here, but for semantic segmentation, we've tried the same thing actually. You can see that the network is literally it's identical.
Cool.
Any other questions, or is it too late?
Hey Matthias, thank you very much for talking to us this afternoon. It's a very nice talk. You mentioned that this occlusion detector network that was very important numerically in the results. So the scenario that you pointed out is that you have one frame, a point is visible, and the other frame, the point is not visible.
Yeah.
So what would happen if in the 2 frames, there is no visible points that you've seen during training? So that could be a scenario, for example, where someone turns completely, so you see their back to the camera.
But you always see the point, right? Like the definition is the center point, like you don't mark the point. It's always the center point. Like in the source frame, always the center point is going to be the query point, so to say.
All right. And okay.
But this point may or may not exist in the target frame. You don't know it for sure.
So this would still be able to work if the person starts like doing 360 spins.
But you do it, the network is just being run between frame pairs.
Right.
So what you might have is that if you do a 360, you just might not find an overlapping frame, but that's a different problem. Like if you have, right? But I guess what I'm trying to say is you might have frames where there's 0 overlap between the 2 frames. Then this occlusion network gives you false, I mean, hopefully it gives you false for every point.
Okay.
Which it's not solving the problem that you get good correspondence in this case, but at least the optimizer is not so confused anymore. Like, otherwise it has to force a prediction where there's nothing there.
Right, right.
And this, we tried this at the beginning, like just when you optimize this in the training, it's very brittle.
Thank you.
Okay, hope it helps.
Great. Well, maybe we should wrap it up there. It's a bit over time. Thanks for visiting virtually. We'll have you back at some point in the real world, I hope.
I hope that real world is going to open up again.
Yeah. And we'll post this on YouTube. I'm going to stop recording now.
Okay, thanks.
Thanks. Take care.